Welcome to the lectures in modern digital communication techniques. So, what we have seen in the previous lecture is the Kraft inequality, which tells us that what are the code word lengths which can be used to construct a prefix free code. If someone tells you that I want to use code word lengths of 1, 1 and 2, then you can clearly establish that it is not possible to construct a prefix free code, because you are going to get 2 to the power of minus 1 plus 2 to the power of minus 1 plus 2 to the power of minus 2. So, that is more than 1. It does not satisfy the Kraft inequality and cannot construct a prefix free code. And that the example that we had for this particular numbers are the code which are like 0, the second code was 1 and the third code was 1 0, which could have been assigned to A, B and C, and where we found that it is not possible to construct prefix free codes with these codes. And what we can now establish is that without verifying whether prefix free property holds or not, by simply not satisfying the Kraft inequality, it can tell us that it is not possible to construct a prefix free code. So, now once we have done that, what we find is that could be of our interest is what is the minimum length on these code words that one could find. Now, this is very important, because all we are trying to do is to find the minimum number of bits that could be used in the source, so that when these bits go out or when these symbols go out into the channel, we take the least amount of bandwidth or least amount of capacity to transmit this information. Now, if you could ask, or if you would ask that why would you ask this question, it takes the minimum bandwidth, we would like to convey the information with as little resource as possible. Now, this discussion is important, because one of the important things that digital communication engineers do is that they want to reduce the resource required. If you think in terms of resource, especially for wireless communications, resource is very, very limited, because bandwidth is limited, power is limited, and along with many other resources as well. So, if you talk of limited bandwidth, you would like to occupy as little bandwidth as possible for one particular source. The reason is you can connect many sources to many destinations, so that you utilize the bandwidth as efficiently as possible. And we will see the term towards the end of this particular course, where you will use the terminology spectral efficiency. So, this is why we are doing this first part of the communications course on source coding. So, moving on further, we would like to find the minimum L bar. So, that means we have to talk about L bar. L bar would be the average length of code words. Now, what we have seen is that the code word length could be 1, it could be 2 and 2. So, if these are 3 code word lengths, if someone asks us that what is the average length of the code word, so we will go back and we will say that 1, the length 1 was for B as for A, and B had a length of 2 and C had a length of 2. Now, if A has a certain probability P of A, B has a certain probability P of B, and C has a certain probability P of C, then one could say that it is P of A plus twice P of B, because 2 bits, plus 2 P of C is the average length of this particular source which has these symbols, right. So, that means we are talking about the average. Now, the question that one can ask is that, well, if you assign a particular source a set of code words, then or code word lengths, then one could assign, or one could ask the question, what is the minimum of all possible averages? So, why we have this question? Because if I have a source which is very which has a large number of symbols in it, right, and these symbols are assigned to certain lengths, right. So, when we say that L bar is the average length for a particular mapping. What we are interested in is amongst all possible mapping of lengths to code word lengths, these lengths to code words, which particular combination gives us the minimum, or rather what is the minimum value. Then one can go ahead and find the mapping which gives this minimum value. So, with the intention that we would like to reduce the number of bits per source symbol. So, if we are talking about the minimum L bar for a prefix free code. Now, when we talk about minimum L bar for a prefix free code, we would begin with a discrete memoryless source. So, when we say a discrete memoryless source, you can go into the definition of discrete memoryless source, but what we have done is almost defined a discrete memoryless source with the examples that we have taken. So, we can say that it generates an unending sequence of x1, x2 and so on. So, these you can say there is an unending sequence, right. It is a source. So, that means it keeps on continuously generating these symbols. So, these are the symbols which are randomly selected, from a finite source, let us say x, which contains A1, A2, AM, right. So, this is the source alphabet. Right. So, these are the symbols. So, x1 could be this, x2 could be this, and so on and so forth, and each source output, that means this x1, x2 dot dot dot, all these are selected with some probability mass function, and probability mass function would be p of x, because this is this alphabet, p of x of A1 up to p of x of AM, right. So, there is a certain probability assigned to these particular symbols. When we say that assigned, it is not actually something that we assign to a source, it is the source inherent nature. So, if we take this particular lecture for example, and we look at all the things that we write, and we try to plot the histogram of the letters in it and normalize that histogram, then we can possibly find the probability of the different letters. One could also find probability of the different words that we are using. So, that means if I look at the source as one which generates these letters for this particular lecture that we are looking at, we are interested in, we will find a certain set of probabilities. Now, if you are looking at some other lecture and of a different subject, then there is a high chance that you would encounter a different probability. The reason being, in this particular lecture we are concerned with a particular subject, and we are using some words more often than if it was a different subject. And the other object or the other reason could be that we are using some particular letters more often. For example, I have used A's quite often, right, and I have used X's quite often. So, if it was not this particular lecture and some other lecture, and people could have used the letters, let us say Z, and they could have used gamma, they could have used alpha. So, there would have been a higher probability of those than these letters that we are looking at. So, it is an inherent nature of the source, right. So, that is of course what we are not assigning, but it is present, and each of these these symbols, they are statistically independent. This is one of the most important things which we did not see till now. We had almost seen the first two postulates. The third one tells us that when one of the symbol comes out, it is independent of what has happened before and what is going to happen afterwards. For example, if we take the example of tossing of this die or throwing of the die, what we find is that the probability, if it is a fair die, of course, when we are playing Ludo, I mean it does not work out, that it often happens for us. This 6 does not land up more often compared to one of my partners. Now, it is very difficult to explain that, but if we take the all possible throws, what we will find is that in that particular game, that the probability of getting the 6 or probability of getting a 3 and probability of getting a 1 over several trials turns out to be almost equal, right. And that means they are of equal probability, and the next equal probability does not necessarily say that it is independent. What we are trying to say here is that once I throw it, if I get a 6, there is no relationship with what is going to happen in the next one, or vice versa. If I have thrown a 6 or if I get a 6, it has no relationship with that whether a 6 has happened before that or whether 1 has happened before that. So, statistically independent would, in other words, what does it mean is that there is no memory in it, right. So, we have talked about discrete and we have talked about memorylessness. So, that means a source what we have already taken, but now we add the term that there is no memory in this particular source, right. So, we are taking a discrete memoryless source and we want to determine what set of code word lengths can be used to minimize the expected length of the prefix free code for the discrete memoryless source. So, we are talking about the set of code word lengths, that means L of A, L of B up to L of, let us say Z, or L of A1, L of A2, L of A3 up to L of A of M, which can be used to minimize the expected length of it, right. So, in other words what we want to say is that we want to minimize the expected length subject to Kraft inequality. Why do we bring in this second statement? The reason of bringing in this second statement is that we are talking about prefix free codes. So, that means we have a discrete memoryless source and we are saying that the codes will be prefix free. So, even if these are prefix free, we have to minimize the length. So, the moment we say prefix free code, we can immediately jump onto this Kraft inequality. So, to begin with this, we will say that let there be these lengths L of A1 up to L of AM, which we have used before, and of course, these lengths satisfy the Kraft inequality. So, that means these lengths already satisfy Kraft inequality because it is a prefix free code. And then we would define L of x or simply L as a random variable representing the code word lengths for a randomly selected symbol. So, that means this could be this, or anything. So, this could take a value. If I have, let us say 3, 5, 6 and 7 as 4 possible lengths, then I could say that capital L chooses any of these values of lengths, right. So, this is basically the random variable representing the code word length selected from this set. Okay. So, now we write the expected value of L for a given code word. What we could write this as L bar. So, this is what we have been writing is equal to E of L. Now, this is the notation we are going to use. E means expectation, and we have already done this calculation in the previous note that we were writing. This is simply sum of j 1 to m, because there are m symbols, length of the jth code word multiplied by the probability of the jth code word following this particular random sequence. So, this we have already calculated in our previous example here. We have already done this calculation. So, that is what we are writing more formally over here. So, this is, so now what we are trying to say is that we would like to minimize this L bar, because you could assign different lengths to different ages, right, or you could assign different lengths to different probabilities. So, we would like to find this match between these two, so that over all possible length sets, that means if L of a j over all possible length sets, which particular length sets would minimize this value, would give me the smallest value of this. So, that is what we can write. So, we say that we want to find L bar min, we would like to find L bar min, which is the minimum value of L bar over all possible code lengths satisfying Kraft inequality. So, to proceed with this, what we do is we take a long sequence x. Okay. So, let x be a long sequence. So, what we mean is that I take a sequence of symbols and I take them x1, x2, x3, x4 up to xn. So, this is what I mean by capital X, and these are of course selected from this alphabet, and they have these different lengths. Now, the number of bits resulting from using the above code word lengths or the above code to encode this long block or to encode x, let us say in short. So, we could say that S n is the sum of these bits, which is length of x 1. So, I have this long sequence plus the length of x 2 up to plus length of x n. Look at this, what I have done is I have taken x 1, x 2, x 3, x n up to x n as a long sequence. So, x 1 will have a length L of x 1, because this is a random variable. So, that is why I have taken L of x 1. L of x 2 will be the number of bits required to encode x 2, and L of x n will be the number of bits required to represent x n. So, for example, if this is A, this is B, then again A and A and A, I would have 1 going by our previous example here. I will take length of 1 plus 2, then I will take 1 plus 1 plus 1. So, that means, if I have a sequence A, B, A dot dot dot, or if I had a sequence, let us say B, C, B, A, B, B, in this case the length of 1, 2, 1, 1 would be taken, in this case 2, 2, 2, 1, 1, 2, 2 would be taken. This sum would be the number of bits, because B would be in this case 1 1 and C would be 1 0 or 1 1, A is 0 0 1 1 1 1, whereas in this case it is a 0, it is a 1 1, a 0 and 0. So, here is in the 1 2 3 4 5 bits in 4 symbols. Here if I take 1 2 3 4 symbols, I have 1 2 3 4 5 6 7 bits. So, this sum is what is being represented here. So, now these L's that you see over here, these are IID random variables, because these x's are IID random variables. So, therefore, definitely the lengths are also IID random variables. So, if these are random variables, this S n we can say it is a sum of IID random variables, right. If it is true, in that case we can say that S n upon n, this ratio would tend to the expected value of L if n is very large. So, using law of large numbers, we could say this as n tends to infinity, and not only that, we can say that this approaches this with nearly probability of this happening is almost close to 1. Now, if you are used to the asymptotic equipartition, then also this result would come true. That means, if I am taking a very long sequence, then the and I am adding up these numbers, the lengths of it, and dividing it by n, what you end up with is that this number tends towards the expected value of that particular sum or the individual numbers, and that happens with probability almost equal to 1, and this happens only when n is very large. So, if I take 4 of them, I cannot ensure that this is going to happen, but if you are going to have it as very large sequence, let us say I take 100 or 1000 or 10,000 such symbols in one sequence, and I do this, then I can find that this number would be almost equal to the average value. That means, the sample mean is almost equal to the ensemble mean. So, you can do it like that. This is a law of large numbers approximately, and if n is very large, this is almost with a very high probability. Now, using this, you can say that L bar, that what you have is basically the rate at which the bits come out of the source, right. So, since because this is the average number of bits. Now, once we identify that this is the average number of bits that come out of the source, then what we can continue on is let P of a j be written as P j, that is the probability of getting this particular symbol or probability of getting this particular length. So, we can say that L bar is equal to sum over j equals to 1 to m. We have already said this in a different way, but we write it like this L j P j. What we had written before is that this is equal to L of a j times P of a j. So, we have shortened this and said L j times P j. Now, what we have is that this particular problem of minimizing mathematically, you can state that L bar min, that means the minimum value of L bar is equal to the minimum value of this sum j equals to 1 to m, let us say P of j times L j or L j times P j, does not matter. So, basically you are trying to minimize L bar, but you have the constraint that you have this values which are given L 1 to L m subject to the Kraft inequality, that means 2 to the power of minus L j, j equals to 1 to m should be less than or equal to 1. So, that means over all possible lengths subject to this condition, I would like to minimize this. Now, this condition that we have over here is because of the Kraft inequality, and what we have said is that this Kraft inequality comes in because we have this prefix free condition. So, we said that over all possible code word lengths which satisfy the prefix free condition, we would like to minimize the code word length. In order to proceed with this, we are going to use the Lagrangian method. So, you can use the Lagrangian technique for this. So, of course, we have a particular relaxation. Now, if you look at this particular problem, these lengths that are there, these are integer lengths. So, it is not possible to do a Lagrangian with integer lengths because you have to take this derivative. So, the first relaxation that we make is we will assume that let these lengths be real values. Now, if these lengths are real values, whatever number we get out of this, could be a good approximation, could be what possible lengths that we can choose from which we are going to minimize. Now, once we get these real approximations, then we can find the nearest integer which is the best match to this and could be our possible solution. So, the cost function we could write it down as sum over Pj Lj plus we use a Lagrangian multiplier and we have 2 to the power of minus Lj is as this particular constraint minus 1. Now, why we take this? Of course, because we are saying that a full tree cannot be minimized. That means, if the tree is not full, what does it mean? The tree is not full means you can shorten the tree. So, if you can shorten the tree, that means the length becomes less. So, if the length becomes less, that means the previous condition it is less than or equal to 1, but now when you have reduced the branch, if you would remember that we had this tree and we said that this length is extra, you do not need this length. So, instead you can draw a tree, right. So, the moment we compare these two trees, what we find is that there were 3 code words in this A, B and C. There are again the same code words in this, but C has a length which is smaller than this and C is also a prefix free code. That means, this tree is a prefix free tree, this is a prefix free tree, but since this is full, what it means is that you will have a length which is lesser than this. That means, the average of this or L bar of this is going to be less than this. Otherwise, we are not having the best possible length combination. So, therefore, instead of taking less than or equal to 1, we will use the constraint 2 to the power of minus Lj sum over is equal to 1, because this is going to minimize it. So, with this as our problem, you could take a derivative of this with respect to Lj. Now, since I have to take a derivative, that is why we said initially that let our constraint be relaxed and we can say that let these take real numbers. Once we solve for it, then we can find a better number, integer number which is matching to this. So, once you take the derivative and set this equal to 0 and use this constraint that we have used over here, we can find Lj's which could be useful, the set of lengths which are going to minimize and solve this particular problem. Right. So, we stop this particular lecture over here and we will carry on in the next lecture with this particular derivation, and we will see that what particular lengths we find would be helping us to minimize the expected length of the code words, so that we can use as minimum number of bits as possible to encode a particular source. Thank you.